Well, we've heard a lot about dark energy in the last 20 years, and this is where it first started. This is a graph of supernovas, acceleration of not of supernovas, but of galaxies with supernovas in them. And the supernovas seem to show that, as you can see, there's just a little bit of pulling away from the straight line. A little bit of acceleration is creeping in, and it's increasing with the distance. This dark energy content was discovered in 1998, and it was considered to be an acceleration term on top of the redshift, which is a velocity term, velocities of galaxies moving away. And what everybody says, it was completely unexpected and without obvious explanation. However, I don't say it was unexpected. As I'll show you, it was not unexpected, and it does have explanation. It's got significant implications for physics as well as cosmology. Now, we need to do a few definitions. For an expanding universe, scale factor R, the Hubble parameter is defined as the normalized rate of expansion, which is the ratio of V over R, the velocity over the distance of the recessional velocity and the co-moving distance of distant galaxies. So it's just simply V over R. The Hubble constant is the Hubble parameter at the present time, because the implication is the Hubble parameter changes with time. And this is defined in terms of the Hubble radius, the radius of the observable universe, as the velocity of light c over rh. And at the present time, v equals h naught r. B is proportional to r, and c r over rh. Well-known formula. So what's the explanation for that? Well, we go back to Einstein's field equations of 1915. And when Einstein wrote down that, he didn't know what would happen to the universe, whether it would collapse or expand, or whether it would stay the same. And he wanted it to stay the same. And so in case it collapsed on itself, as gravity would seem to suggest it might, he introduced another term. You see the lambda on the bottom line is an additional term added to the g mu nu. And that's called the cosmological constant, and it's a term added to prevent what he thought was probably a finite universe from collapsing in on itself. Einstein's equations were solved by Alexander Friedmann for the case of possible universes. And he found there were three depending on the universe density. So those are the graphs down below. If you've got a density less than the critical density, it'll expand forever. That's the first graph. If you've got the critical density, and we'll explain what the critical density is in a moment, it'll expand towards a limiting value, and that's the graph on the right. And if it's more dense than the critical density, it's the middle graph, and it will collapse in on itself. So at the critical density, the universe will be, the critical density is the one where the universe is exactly flat or Euclidean with no curvature. Curvature parameter equals 0, the curvature parameter in Einstein's equations. So Friedmann's first equation says that if there's no cosmological constant, which he didn't include, then the following equation works. The Hubble parameter squared, h squared, equals 8 pi g over 3 times rho, which is the mass density, and minus kc squared r squared, which is the curvature term. However, if there's no curvature, then the critical density without a cosmological constant is exactly 3h naught squared over 8 pi g. And we use a parameter, a convenient parameter called omega, which determines how close the actual density is compared to this critical value. Rho over rho critical is called omega, and that determines the evolution and fate of the universe. And if omega equals 1, then the density equals the critical density. So this value of omega equals 1 has a special significance. there's a clear separation there between a flat or Euclidean universe from a closed universe and an open universe. Now, from about 2000, we've known that the experimental value of the omega has been converging towards the exact value of 1, the exact value for critical density, which implies that the universe is flat and possibly infinite. It's hard to see how it can be flat without being infinite. And if it's got the critical density, you're also inflating your cosmology. If you go in for the Big Bang theory, then you'll get inflation on top of it. You'll get acceleration on top, and that's against what people believed before. Everybody believed before that the universe would collapse in on itself over a long period of time, and it was a closed universe. That was the general feeling. Another thing that the critical density and the flat universe means is that general relativistic calculations are taken to the Newtonian limit. We simply incorporate energy into the mass term and we get purely Newtonian equations. In fact, we can forget about general relativity. It just becomes purely Newtonian. So the expression rho crit equals 3h0 squared over 8 pi g is equivalent to 3v squared over 8 pi g r squared, which is simply another version of the Newtonian relation potential energy gm over r equals kinetic energy half v squared for a there should be a mass on the right hand side. No, there shouldn't. Those equations are okay, but those are for unit mass. But the mass density doesn't have to be solid matter, it can be energy as well. So if we have energy, we replace rho, the mass density for solid matter, as rho plus 3p over c squared, where p is a kind of pressure, so an energy density from what we might call a vacuum term. First of all, it might be a positive pressure inward, so acting in the same direction as mass does. For example, if we have a significant amount of radiation, so we can include a term like that into the rho term, and it doesn't change the significant meaning of omega. So that's a pressure acting with the density. Here we will assume that k is 0. If we include a cosmological constant or a vacuum energy term with negative pressure, then we have another inclusion, minus lambda squared over c squared over 3. Now, this doesn't change the definition of omega, but it has major physical consequences because this one acts against the density. And it seemed that this is the kind of term that was discovered in 1998 as an outward acceleration in the redshift velocity of distant galaxies. So this dark energy can be incorporated into omega as the component omega subscript lambda. But it's seemingly an unexplained phenomenon. And when we saw the early values of its magnitude, which were in the 70% of the total energy of the universe, 71.4 to 74, then there was no obvious clue to its origin. It was just another term with a large percentage of the energy of the universe. However, newer values give an indication that just as with omega itself, as omega has a critical value of 1, there's a particular critical value of omega lambda with a precise physical significance. And new data seem to suggest it might converge on this critical value. Now, this, to my knowledge, has not been noticed by anyone else, that this particular value would be a critical value. So the most recent data we have about the percentage of dark energy in the universe is from the Planck satellite, published in March 2013. And there were various fits they did with various types of data. The pure information first, then with lensing, then with the previous W map, and then just the temperature anisotropies. And these are given to 68% confidence limit, so there's a reasonable amount of leeway in this data. So you can see the values are around 0.68 plus or minus a small amount, something like 0.02 to 68% confidence. So that's the first standard deviation, is that. And some of them are slightly higher, some of them are slightly lower. I think the average is taken is about 0.683% of, so that 0.683 is the fraction of omega that is due to dark energy, I'm sorry. Now, data like that give us an intriguing possibility. It's very close to 2/3 of the total energy of the universe. And if it should happen that 2/3 turns out to be the exact value, then a simple calculation will show something really interesting develops. So let's do that calculation. Let's suppose that the rho vacuum over rho critical, that's the density of the vacuum energy over the density of the critical density, the density of the universe, is 2/3. Exactly. So roughly 67%. Very much within the order of the information that we have. So if that's the case, then we can immediately write the vacuum density as h0 squared over 4 pi g, which is equivalent to a dark energy density or negative pressure minus P equals h0 c squared over 4 pi g. And a corresponding cosmological constant, interestingly, equals 2h0 squared. And we can incorporate the P or the lambda into Friedmann's first equation and again make the curvature 0. And that will give us the second equation down there with rho plus 3p over c squared. And this time P is negative. Or into the second equation to give us an acceleration over a distance equals 4 pi g over 3 rho plus 3p over c squared. So if we take the uniform and isotropic Hubble universe as the first approximation with mass 4 pi g rho r cubed over 3 as usual within the radius r, then we can interestingly express this in terms of force on a unit mass, which combines the effect of gravity inwards and dark energy outwards. And we get the equation down below. So if we write the force on unit mass in that way, we can express the acceleration responsible for the dark energy as, and this is the significant formula, which only comes out of the critical density being 2/3 of the total energy density of the universe. A equals v squared over RH, acceleration equals h0 squared r. And that's very significant because it means that the acceleration and the velocity are related directly and they're not independent information. So the acceleration observed in redshift, given that 2/3 critical density, like the velocity, depends only on the Hubble constant and the distance. And so one could suspect that it's part of the same process that produces the redshift velocity. And if we take the acceleration and integrate it between limits v and r and v and 0, 0 and v and 0 and r, we get the exact Hubble redshift law. V equals h0 r over c equals c over rh. So we get the velocity law from the acceleration, assuming that it's 2/3 of the energy density of the universe. And we haven't done any conjecture or speculative element whatsoever, and no modeling of any kind. It's just been directly obtained solely from the data, assuming that the data means that the density of the dark energy is 2/3. Now, if we take the data as it stands today, the equation is valid to within the experimental confidence limits of 68% and it's, say, within a factor 1.02 plus or minus 0.02. This is so close to being exactly true and of such exceptional physical significance, if it is, that we're justified in saying that the test of its exact validity should be one of the aims of future probes. So when we next send up a satellite to measure the parameters, then we should be using this as one of the tests. Is it exactly 2/3 or very close to it? And if we compare it with the Boomerang collaboration of 2000, which found the flat universe, then they had the 95% confidence interval for omega was between 0.88 and 1.12, which is a lot further out than this is from 2/3. And they were immediately able to claim with complete justification that this provided evidence for a Euclidean geometry of the universe. And even today, omega equals 1 isn't established to better than about 1%. And it's on the high side. So Planck collaboration 1, which includes some data from lensing, constrains, quote, departures from spatial flatness at the percent level, unquote. That is omega k equals, that's the departures equals minus 0.0096 with 68% confidence limits. So it's a total omega of 1.0096, and then with those errors, the statistical and the systematics. Now, as we know, the force of gravity involving the bulk of mass in the universe is the Newtonian attractive one proportional to 1 over r squared. And the force of dark energy is a repulsive one proportional to r, if you remember the formula that we used. And in physics, we find that these are dual laws, and this concept goes straight back to Newton in the Principia. The dual laws, he did most of these calculations, assuming first that it was 1 over r squared and then it was 1 over r. And then finally selected it, the law that it was on the basis of just one or two things that were noticed. And you can replace these dual laws by a simple transformation. And I think there are about 5 sets of such dual laws. For example, proportional to 1 over r to the 4th, and proportional to 1 over r to the 7th are dual laws in this way. And these two are the only laws of force which can maintain stable orbits, and there's a theorem by Bertrand about that. So we consider the physical significance of the formula A equals h0 squared r to be due to the fact that the velocity term can be derived from the acceleration, implying that the acceleration, however it originates, is responsible for the velocity. Now, if this is true, then we have to look at our models of cosmological evolution. We can't just assume it's just an additional extra. It's an important factor in it. And there's another equation which we can derive directly from the same starting points, and again without any hypothetical or model-dependent input, which suggests even further significance. And this is about the inertial properties of matter. So why does mass have dual properties of inertia and gravity? Charge doesn't have dual properties. It only has attractive and repulsive forces. It doesn't have something equivalent to inertia. Though it produces inertia, it isn't intrinsic to charge. And the question is, would a body have these inertial properties if the rest of the universe wasn't present? Well, Mach in 1883 thought that wasn't so. He said inertia is caused only by the presence of the rest of the universe. It's called Mach's principle. Now what we're going to do is have a look at a way that people calculate from general relativity. And you can calculate gravitational waves this way, and Heaviside did it before general relativity. Calculated gravitational waves by assuming a Maxwell's set of equations applied to gravity. He didn't know what the velocity would be, but guessed that why not take the velocity of light as the velocity. So you can conveniently explain many aspects of general relativity, including gravitational waves, by the presence of velocity of light, meaning that we have a magnetic component of gravity in the same way as we have one of electricity. You set up a set of equations exactly similar to Maxwell's equations, and that serves in the first approximation very well, and it's used quite a lot for various effects. Which means that any equation electromagnetism has a corresponding one in gravitational theory. And Dennis Sharma, who was the thesis advisor of Stephen Hawking, produced a Machian theory of inertia in 1953, assuming that the magnetic component of gravity was responsible for inertia. So we can write the acceleration in the form a equals dv dt and write it as c squared r over rh squared. That's our version of the acceleration. And then if we follow Sharma, we can look into the possibility of explaining inertia along the lines of Mach's principle, using a gravitomagnetic inductive force between two masses with relative acceleration. It's just really applying special relativity to it. It could be derived from general relativity, or it could be derived from special relativity, because at this point it doesn't matter. And inertia then would be a long-range force increasing with distance. And inertia, of course, is a repulsive force, not an attractive one. So if you take, there's a long-range inductive force between charges from electromagnetic theory, which we derive from Faraday's law of induction, F equals G over C squared, and then E1, E2 sine theta dV dt. And we could do exactly the same thing with masses and create a completely parallel equation below, with masses replacing the charges. Now, Sharma thought that if we use this force, and if we assume isotropy removes the angular dependence, then the inertia of a body of mass m, say m equals m1, could be attributed to the action of the total mass within the observable universe, the universe within our event horizon, which will be specified by the Hubble radius. And we would then make the inductive force equation equivalent to the Newtonian inertial equation, F equals kma, with k a constant, and a dv by dt. And so you can write down an equation for the inertial force on a unit mass due to the entire mass in the Hubble universe, and it would be the equation below. Now that's what Sharma did, but one can go further than he did. You can say that, well, inertia is a measure for defining a unit mass, and gravity is another. And gravity is the one we normally use when we use a balance. And we can make the connection via the equivalence principle. So we suppose the mass mh defines a radial inertial field of constant magnitude from the center of a local coordinate system. And so at the same time, we're going to use the principle of equivalence to equate the magnitude of this to the gravitational field gmh over rh squared. And this is independently of the local coordinate system, defines a unit of gravitational mass within the same event horizon. So effectively, we're defining a unit of gravitational mass to be equal to a unit of inertial mass within the Hubble radius event horizon. So we can make that equate those two equations. And if we look at that and we do a couple of bits of cancellation, we find it's exactly the expression for the acceleration, which would result if the dark energy constitutes exactly 2/3 of the total energy of the universe. So if we have an exact value of 2/3 for the dark energy, then It links the dark energy and the Hubble redshift as aspects of the same phenomenon, but it might be of additional interest in connection with Mach's principle and the origin of inertia. And again, we could expect possible cosmologies to be necessarily constrained by fundamental laws of physics. And in my opinion, if cosmologies don't obey laws of physics, or they don't suggest the reason for laws of physics, then they're no use at all. They're just archaeology and not physics. So, for example, the Machian origin of inertia would allow a universe to evolve by creating inertial mass. Not necessarily actual matter, but energy of some kind, at the same time as its space-time structure, with the creation process also generating the force which drives its evolution. I'm not suggesting that this is a correct theory. I'm just saying that's one example of how one could think about it. And I have my own views on the universe, but I'm prepared to listen to others. So it's significant that the equation of the gravitational and the Machian inertial forces give us the acceleration that we derive from 2/3 of the energy density of the universe. It doesn't require the development we suggested. These are possible contexts. None is needed to generate the equation, and the form of the equation itself is significant. So if I go back to that slide, that first equation there is the same as the second equation, with just a couple of terms multiplied on each side. And so that first equation is as correct as the second equation. However, if you go on a prior prediction and then it leads to experimental confirmation, that's one of the strongest arguments ever available for any theoretical construction. And in the present case, there is also a prior prediction, and a very long time before the dark energy was actually found. So a version of this calculation is done in reverse as part of a larger study. So I start with the Machian argument and end up with the 2/3. And at the time when this was done, the values of omega lambda looked less favorable to its conclusion because we were still getting things like 74%. But that's in 0 to infinity and several earlier works as 2/3. And that itself was preceded by a lot of calculations deriving the redshift acceleration as h0 squared r on the basis of assuming that a flat universe was true. And many of them predate the experimental discovery of the dark energy. One of the most accessible is from a book called A Revolution Too Far, which I published in 1994. And it's not the earliest derivation by any means. A long time before that, I was deriving this A equals h0 squared r. And there were probably about 12 or 15 published versions, one form or another. And so I've stuck to this even when the data didn't look as favorable as it does now. So in this predictive context, the dark energy would seem to have a possible explanation in both physical and cosmological contexts. And the calculations seem to imply there may be a critical value for omega lambda, just as there is for omega. It's within the limits of the data that the Planck probe has already produced. And maybe future experimental findings will converge on this value, just as they converge on omega equals 1 for the total energy density. Now, even if you got very close, you require explanation in the same way as values of omega close to 1. As soon as it became anywhere near 1, people thought it's too close for coincidence, even before they could establish the exact value. And so it's worth looking at that concept. It's interesting to see how the constraints and other cosmological parameters are affected by applying this exact value for the dark energy density to the Planck data. If one went back to the Planck data and impose this value, what would that constrain other cosmological parameters to? And maybe if we didn't get an exact value of 2/3, but very, very close, maybe that would say that the universal isotropy and uniformity which are assumed in this calculation might not be true. It reminds me of the Newtonian calculation of the shape of the Earth, which was like an orange shape, an oblate spheroid, and there was a figure of the Earth given of about 1/230 or something. Maybe it was 1/290, when the real figure, as we now know, is about 1/230. Now, the reason why that was why there was any discrepancy at all is because the Earth is not a uniform sphere as was assumed for the calculation. The Earth is a very complex structure, and of course deviations from the values predicted for a uniform Earth would subsequently then be used to find the actual structure of the Earth. Nobody said, oh, the idea is no good. What they said, no, the idea is good. What we've got to do is get beyond this assumption of uniformity. And so that's the end of the presentation, and I'm ready to take questions.